So in this video I'm going to take a look at different circuitry components and looking at their different characteristic graphs. So first of all, let's look at the most basic one, the ohmic conductor, and you can recognize it because in a circuit you'll see a symbol that looks something along those lines, or you may see it in the form of a variable resistor as well, which you'll see with a line through it, a bit like this one. The key things for it to be an ohmic conductor is it needs to have current being directly proportional to the potential difference applied across the component. So essentially what you'd actually be doing there is you'd have a voltmeter like this one, measuring the potential difference across the component, and you'd have an ammeter in series here, taking measurements, and you'd find those two were directly proportional to each other. So that's the starting point. And then actually it's about thinking, well, what does this graph show you? So if we have a look at these two lines, we've got the red one and the blue one. So if we look at Ohm's law, we can arrange it in the form where resistance is V over I. And if we look at our graph, we can see that the gradient of the graph would be I over V. So essentially what you're going to find is that the resistance is 1 over the gradient of this graph. So this red line here is much steeper, so it has a larger gradient. So 1 over a larger number would mean it has a lower resistance. So this red line actually has a lower resistance, and this blue line has a higher resistance. And as a side note, the power, which you can calculate using IV, is going to be the area under the graph. So if we want to know what the power dissipated at a certain potential difference is, you'd be looking here and you'd be looking at the area under that. But like I say, that's a side note. I'm more interested in looking at the gradient and how that impacts on resistance. So that's an ohmic conductor. So let's move on. The next one we'll look at is a lamp. So you'll recognize these because they're the things that give you light in your circuits. But their characteristic graphs have two key sections which you need to be thinking about. So they tend to have this straight line section in the middle, so they look, for all intents and purposes, like an ohmic conductor between these values here, and it changes from light bulb to light bulb exactly where those values are. This is important when you're thinking about an experiment to determine what kind a component is from its IV graph, because you need to think about the range of values which you're going to take. But let's look at this. So exam questions on this topic tend to be a 2-mark type 1, simply because they're expecting you to split the graph into two sections. So what they're looking at is the significance of this point here. So when V is less than this VP value, it's a straight line. And what does that mean? It means the resistance is constant, because the gradient is constant and 1 over the gradient is resistance. So in that section your resistance is constant. When V is greater than VP, the gradient is decreasing. So it's going down because you can see it's flattening off, which means that your resistance must be going up, since the resistance is equal to 1 over the gradient, which makes sense because essentially at this point your light bulb's getting quite hot, which means there's going to be more resistance to the flow of charged particles moving around your circuit, which you'll see in the form of an increased resistance. So the next one we're going to look at is a thermistor. So this is a type of semiconductor. So what a semiconductor means is that you can change the the resistance of your component by changing the conditions in which it's operating, so like changing the temperature, changing the light intensity, that type of thing. So with a thermistor, as you increase the temperature, there are going to be more charge carriers available, and so you can more easily carry a charge, which you'll see in terms of a lower resistance. So if we look at the blue line, the gradient is clearly a bigger number, so it's an increased number compared to the red one, which means that your resistance must be lower. And if we look at the red line, the gradient is a smaller number, which means your resistance must be higher, because 1 over a smaller number gives you a bigger number. So if the resistance is higher for the red one, this must be cooler, and then this blue one must be hotter. So at a given temperature, the thermistor will look like an ohmic conductor, but the key thing is you can change the gradient of your line by changing the temperature. So let's look at a slightly more useful graph for this. If we plot a graph of temperature against resistance, so as we change temperature, looking how resistance changes, so we're going to put our temperature on the x-axis, that's the thing we're changing, and the resistance on the y-axis, because it's the thing we are essentially measuring. And what you find is you get a graph that looks a bit like this. So as you increase the temperature, your resistance decreases, but it's not a linear relationship. You get this kind of decay type graph. So this is some sort of logarithmic relationship going on here, which we don't need to get into. It's more about knowing the profile of your thermistor. So let's move on to another component. Looking at LDRs, or light-dependent resistors. It's another type of semiconductor, but instead of changing temperature in this case, you change the light intensity. So again, as you increase the light intensity, you release more charge carriers, so you get a lower resistance. So just like before, you get this type of graph that looks something like this. So one of the things you might need to think about in designing an experiment is actually, well, how could you change the light intensity? And that's quite a nice easy one. If you move your device further away from a light source, the intensity reduces. It's an inverse square law, but you don't need to worry too much about that. But in terms of thinking about how you can change light intensity, it's about the distance between your source of light and your LDR. So the last component I'm going to look at is the diode. And the first thing you always need to know about a diode is whether it is forward or reverse biased. So this is what a circuit component looks like, and the arrow direction essentially tells you which way your diode is facing. So this one is facing that way. So if current is going through it that way, it would be forward biased, and if current is going that way, or trying to go that way, it would be reverse biased. So there's 3 distinct sections you need to know about for the diode. So the region of infinite resistance, the region of reducing resistance, and the region of fixed resistance. So this is your region of infinite resistance in the reverse bias zone. So there's nowhere in here in which there'll be a current flowing. It's an infinite resistance. So when you get to a value of 0.6 volts, typically for a diode, you get this region where your resistance is reducing. So we're talking about in this section of the graph, sort of like here. So you get the region where resistance is reducing, and then in this section here, you've got your resistance being a constant value, because you've now got a straight line graph. So diodes are quite useful in protection type circuits to prevent large currents flowing. But quite a common mistake people make is going where it has this region where the graph is, it's an ohmic conductor, or it's directly proportional, and that's not correct. So something to watch out for and remember is that an ohmic conductor is one in which the current is directly proportional to the potential difference. But you can clearly see if you look at this straight line section, it wouldn't go through the 0, 0 point, so it would never be directly proportional, so it can never be an ohmic conductor. So something to be very watchful of when you're dealing with diode type circuits.